Yep. Okay, great. Yeah, thanks for coming. So, again, we'll go through the standard way we go through this. I will go through each section, and I'll ask any questions, and afterwards we can revisit it. If we've gone through the entire thing, and there's no question. So, I guess first of all, 5.4 elliptic curve pairings. Any questions on this? Sorry, the 5.4, sorry, embedding degrees. Any questions on this? Anything we want to talk about on this particular section? Just slowly scroll down. Okay. Elliptic curve over extension fields. Last week we talked a little bit about extension fields. So here, essentially, what we've been talking about extension field were not last week, last week on fields, chapter 4, I believe. Yeah, here extension field refers to the prime extension fields. Um, yeah, extension fields. Oh, actually, before I continue, I does anyone here tried to implement elliptic curves? Um, if you did, do open a PR to the repo that I've shared. I'll share it again. Um, Later in the Telegram group. By the way, if you're not in the Telegram group, let me know in the chat. I'll just speak up. I'll share the link to you. Yeah, in the chat, and yeah, so you can join. So yeah, for those that did try to implement elliptic curves, so that's our last week homework, self motivated homework. For those that did, you are free to open a PR to our repo, and I'll be looking at those and giving you some feedback as well. I'll also be working on implementation myself in Python. So yeah, if you're interested, do it. It helps us learn. Helps some of us, right? And for me, at least, it helps me learn a little bit more into the details of what we're going through here. Implemented with cursor, but great learning to see. Yeah, 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 yeah. It's okay if you use vibe coding tools. Um, as long as you feel like you learn. I do recommend not doing that if you try to learn like the nitty-gritty details. I do personally use AI assisted to help me plan out like the pseudocode. Those helps a little bit. Yeah. Some equations are hard to do. Yeah. Okay, so so let's get back here. Yeah, do implement. So this week as well, our homework will be just trying to implement pairings as well. So last week homework, I think next week we'll go through all of the things we try to implement. Yeah. But anyways, okay. So let's see. I think there's a question for ZK. What high and low embedding degree means and how to pick the best. Um okay, so what does it mean? Well, embedding degrees here. Okay, let me find my words. So what's a good way of let me check my notes. What's a good way of explaining it? So a moment. Okay, so embedding degree here. Well, essentially, it's to do with, well, to a certain extent, at least. And from my understanding, it's very much to do with the what's that called? Sorry. It's very much to do with, well, how Well, the definition is it's the smallest integer and such that, R is divisible by Q to the power of K minus one. And embedding degree is K, right? So well, it's well, so to say, it's to do with what you want your curve, like what property you want your curve to have, or what structure your curve you want your curves to have, as is with a few of the things here, like torsion, the torsion group as well. Um, well, I don't think it's like torsion group. It's necessary that it's also like a thing we want, for snarks. Embedding degree, in this case, you you want it to. Well, you choose the not the best. I mean, you usually want to choose the smallest. So, you want the smallest one, which is calculated through this. In a way, it's kind of brute force. I'm not quite sure if there's a non-brute force way or brute force way of calculating this. This is essentially the method. You basically increment until you find some k that's divisible by r. Oh, sorry, r is yeah, r such that is yeah. I think it's divisible. Do I say that correctly? Yeah, I think yeah, such that r is divisible. Yeah. So yeah, this is how you find. So like for example, they give the example for this. So in this case, yeah, the order of E11 F5 is 9, and since the Bernoulli prime, they'll take the factor of 3, and then from that they will find essentially what's divisible by r such that find a k that is divisible by r. Sorry, yeah, I think that's the correct. Okay, so such that qk minus 1 is divisible by r, and in this case, they just go through one by one. So 5 to the power of 1 minus 1 equals to 4, and this is not divisible, but this is divisible, right? So that's how they find it. They want to find the smallest number in this case. Uh, I'm not sure if there is a, so to say, best. I think yes, the smallest is essentially what we want to find. Yeah, but from what I've learned and understand, well, you usually want I think depending on what properties you want your curve to have, you want to choose a curve with different embedding degrees. I think in the case for pairings, if you want a smaller embedding degree, I might be wrong on this. I forgot what I've gone through. I've done some reading on this. But if you are using, or if you are working with non-pairing curves, um, you might want to choose a different, like a curve that has maybe higher embedding degree. I'm not quite sure on this, but there is something to do like the embedding degree determines there is some property that comes with this. Um, yeah, and to choose a curve that has slower or higher embedding degrees, essentially, well, it depends on what you want to do. For Snarks, I believe you do want a smaller one. Yeah, I don't think that fully answers your question, but yeah, that's from what I've understood from going through this and some external material. Um, Let me check if I noted it down somewhere. Um, adding degree. Book. I don't think I have, unfortunately. Yep. Okay. Yep. Smallest embedding degree about why pick curves a specific number of K, like why 12 in BLS. Um, specific number of embedding degrees, you mean? Wait, where's the BLS one? Is that in the book, the BLS, there's 12 embedding degrees? Let me check. No, example. Okay. Um, I I see, I see. Ah, okay, I get what you mean. Um, I don't think it's specifically choosing an embedding degree of like the magic number 12. But I might be wrong. I might very much be wrong. Um, I think it's choosing a small embedding degree in this case. But yeah, I may be wrong. It might be also be related to some security concerns, like security factor. So I'm not quite sure why it specifically chooses 12 for BLS. Mm, but I believe generally speaking, when it comes to pairings, we want small embedding degrees. Yeah, yeah, probably something related to that. Because, for example, if you like here, they actually talk about it as well. If you do choose like a big embedding degree, right? You can't like it's going to be hard to calculate later. I think they talk about it in Torsion Group probably. Yeah. So if you choose something that has like a huge embedding degree, there are some calculation that is harder to do when we want to do pairing. Um, yeah, that's why. Yeah, you might be very much correct on that. Usually these parameters are chosen because of that. Oh, fun fact. I think so. There is a Dan Bonnet talk up there that talks about pairings, and fun fact. This specific curve, the parameter for this is chosen based on like the given reason for this, like choose like the parameters for this is not really chosen via um I think you should check out like the video. The video talks a little bit more about more how like this the parameters for this, the seed for this is chosen. And it's pretty funny that there's not too much reason given for how the uh how the seed is chosen. I'll share the link later. But yeah, that is a pretty interesting video. Anyways, okay, where were we? Yeah, so embedding degree, ideally small for pairing purposes. And if you are not using it for pairing, this matters slightly less. Um, yeah, so usually that's why. Yeah, that's what embedding degrees are. As for why we chose a certain embedding degree, that I'm not quite sure. But generally, pairings, we do want some smaller embedding degree. In this case, it helps with calculation. So I think we were in the curves over extension field. Yeah, again, stop me for any questions and all that. Actually, I'll just share the video link now. Um, moment pairings in cryptography. No, wait. The video is called Pairings in Cryptography. I'll share it here. Yeah. Yeah, anyways. Okay. Stop me for any questions again. I shared the link in the group. So as we are going through, okay, elliptic curve over extension field. So any questions on this? Remember what's prime extension fields, hopefully. Um, yep. We'll talk about a lot about tiny Jobs curve, which is a very specific curve that it's used as an example here. So that's also mentioned quite a lot, I think in previous sections as well. Okay, let's continue. Full torsion groups. Any questions? I think in torsion groups, we do talk about why specifically embeddings is quite important here, if I'm not wrong. I recall seeing that, but yeah. Any questions with torsion group? So yeah, here. Oh shit, sorry. Where is it? Okay, there we go. Let's go up a little bit. So the 5,000 group over this is equals to the 5,000 group or tiny jab jab over 5. So this is actually talking about so what here it's happening. I think I'll go above it a bit. So they were actually calculating a torsion group for baby tiny jab jab, sorry, not baby jab jab, tiny jab jab. Um and here and here what's happening is they are calculating tiny jab jab over this prime extension field. Um and the property that we see here is essentially the subgroup. So the 5,000 group for this extension field is equal to the 5,000 group of the base field. And essentially, this just means that you, no matter like the R1,000 group of your extension will always be equals to the R1,000 group of the base field. Um, yeah, that's essentially what it's trying to say here. And here we see actually in regards to embedding curves, sorry, embedding curves. Sorry, in regards to embedding degrees, um, to find R torsion, you need to compute embedding degree, and you can't compute the R torsion of this for SCCP 251 6K1 because the embedding degree is way too huge. And yeah, and that essentially means that when you want to use like when you do calculate the R torsion group, which is required in pairing groups, um, it's going to be very huge, and thus not efficient. That's why I think pairings we will usually use curves with small embedding degrees because it allows us to calculate if more efficiently. Yeah. This means that the embedding degree is very large, which implies the field extension is very large. And in the case of this, such representation had k-many entries, each of them 256 bit. Without any optimization representing such an element, we need k times 256, which is insane. So it follows that it is not only infeasible to calculate, but yeah, to write down the single elements of the group in general. Yeah. Okay, yeah, that's essentially R torsion or full torsion groups. Full torsion groups refer to the entire thing. R torsion group, well, okay, yeah. And R torsion group refers to the subset, essentially. Yeah, the full R torsion group is everything, but there's also like a lot of subgroup. We still call them torsion group. Okay, anyways, that's all about torsion groups. Pairing groups, any questions on this? Here is essentially where it's actually talked about, where G1, G2 is talked about for pairings. Recall pairings in here. Let me just click back to pairings. I believe it's here. Yeah, recall pairings, we have this, right? This is what pairings is. Some tree group, community group, G1 maps, like G1 pairing map is function G1 x G2 mapping to G3, right? Function takes the element from G1 and G2 and maps them to G3 such that bilinearity property holds. So yeah, pairing groups, yeah, essentially talks about how we get G1 and G2. Any questions on this? No? Then we'll go down. Okay. Oh, so much to be clear about for full torsion, R torsion group. I think it's more okay. So for this, it's more correct to say full R torsion groups and R torsion groups. Um, yeah, I think that's a little bit more accurate. Full R torsion group. Well, okay, full R torsion group. It's every hmm. Okay, full R torsion group essentially it's the R torsion of the curve. Every single okay, let's go a little bit into R torsion group. I can't really just go. Yeah. So again, R torsion group, essentially we define it as given some points, um we take we essentially compute some set of points RP, sorry, such that RP is equals to infinity. This is infinity. Okay, so we have an infinite point, and this essentially, well, how do I put this? Yeah. So okay, let's just remember we define R logarithm as like EFR, so elliptic curve over some field. So R will result in a set that the points is in this elliptic curve, and R times the points, each of the points in this set will be, just click here, will be equals to infinity, right? That means that um because R is a factor of n, what this also means is essentially when you have this R, like when it meets, it has this factor of R, the this these points will essentially disappear. It disappear when given some R that you choose here, like 3 torsion. It disappears when R is 3, right? The points that appear here. So for example, okay, so this is 3 torsion, right? So these disappear when R is 3. Like when R is 4, it will be another set of points, and those will disappear when R is 4. But in this case, everything here will disappear when R is 3. Yeah, so full here, what full here means, essentially, so okay, so let me find an example. No, okay, is it this? No. Let me see if I can find another example. R torsion. Give me a moment. I don't have an example here. Okay, so what exactly is full? Well, when you calculate some E for some torsion, some R torsion group, right? So this one, okay. When you calculate some R torsion group, you can calculate over, well, so the elliptic curves over some prime field, we can calculate the R torsion of that and its extension. Usually when you calculate over that prime field's extension, I mean it's still going to be the same subset of the base field itself over the extension. When we talk about full here, it just means, I think, so the full R version group is essentially when you do some calculation on the field, the electrical over the extended field of their bending degree K. Um, yeah, I think that's what we call the full Gaussian group here, full R Gaussian group here, because you can also calculate the R Gaussian group on any other thing. For example, the non, like the base elliptic curve over some field, not over the base field, not the extension field. That's an R Gaussian group, but we specifically call the calculation on this the full R Gaussian group. Um, I believe it contains all the points. I'm not quite sure. All the possible R torsion, the points in the possible points in the specific R torsion group. Like yeah, if I'm not wrong. So full just well, full just mean I think full. It's called full because it contains the possible all the possible points in this R torsion group specifically. If you calculate it on other um, extension, it might result in something different. Curve extension is equals to ER. Oh, oh, actually, it's explaining it here. Yeah. Does that help? That contains a full subgroup type. Uh, Not full subgroup. All the possible points. All the points in this are okay. For example, okay, let's look at this. Okay, so this the embedding degree yeah, the largest like the embedding degree is 2, right? So this torsion group, the torsion group calculated here contains all the possible points for anything based upon this elliptic curve over the base field. I don't think that's a very good way of explaining it, but it contains all possible points. If you were to calculate, okay, if you have this, right? If this calculating the torsion field, R torsion on this, will give you all the points that it's possible if you calculate the R torsion for, well, in this case, there's only one other elliptic curve in this case. Well, any other extension to be fair. Yeah. So if you calculate, let's say E11 F5, the base field, um, the R torsion for that, it doesn't contain all the possible points. But if you calculate this, you basically get everything. So that's why it's called a full torsion field, I think. It's not full subgroup, but it just all the points in all the subgroups. I suppose that's the correct way of saying it. Yeah. Oh yeah, all the points in the subgroup. All the possible points in your subgroup. Yeah. Okay, great. Ah, I did not script this, so maybe next time I should script this a little bit so I can answer with a little bit more clarity on the school. But anyways, okay, let's continue. Okay, I think I was at pairing groups. So pairing groups, any questions on this part? So in pairing groups, we use R torsion to calculate our G1 and G2, with the only difference being, so both of them come from the torsion group, the R torsion group of the elliptic curve, specifically the full R torsion group. So you need to calculate the embedding degree here. And the only difference is that the Frobenius map, um, the result of this, we define it as P times the points itself. Yeah. So G1, the difference between G1 and G2 is this essentially. Yeah. Any questions? This is actually so E11. So using this example, right? This is actually E11. Okay, this is the tree torsion of elliptic curve 1, 1. This is the parameters for your elliptic. So this is specifically the parameters for shortwise Strauss curve here. Let me just point. So A and B for this formula. Okay. Um, Let me just go back to pairing groups. Specifically that. So let's okay. So when we say E1, the tree torsion group of E11, right? Elliptic curve, this elliptic curve, we are actually so we are actually calculating based on this elliptic curve over the extension field of F5 um to the power of 2. F5 squared. Yeah. In this particular case. That's why you see extra points here, which is yeah from the extension field. Originally, I believe the elliptic curve only have these fields. Yeah, maybe a little bit more, but yeah, originally it only has these few fields, and not so I guess these few fields and not these fields with the additional variability. Yeah. So this is actually calculating based on elliptic curve of the extended field. Um, yeah, that's why it's a full R3 torsion group in this case. Anyways, let's continue. Any questions? Yeah, see. Also, this is just choosing G1 and G2 using Frobenius endomorphism. Uh yeah, if you can try to implement this, we'll talk about it next week. Let me just scroll down slowly. Stop me if you have any questions. So, okay, that's all about pairing groups. Well, pairings. Any questions here? Emilius algorithm. There's a pseudocode here, so you can also try to implement this and yeah, play with it. So the well pairing questions here. Okay, so let's get to the next part. Hashing to curves. Specific. I mean, I think it's just going to try and increment hash functions. Yeah, this goes into how you might hash your values into a curve, and yeah, essentially it just increments the value, and if the value fits into the curve, if it doesn't fit, we increment, and if it fits, we accept it. How to know if a curve is pairing friendly? That is a very good question. How to know if it's pairing friendly? Well, um, from what's here, you want a curve. Okay, from what's here, there is also things that probably, well, it's not really talked about here. But how to know? One of them is you have a small embedding degree, hopefully. Um, you you have some, yeah, you have a small embedding degree. You also have you have some cofactor usually, because that allows you to do, well, the calculation for pairings easier, cheaper, more efficiently. Um, that's one of it. Hmm, what else? I think embedding degrees is one of the factors that decides that. Um, One of the things is also well, it's usually, so this is the one of the factors I believe, but I think generally you essentially want something that allows you to calculate pairings cheaper. That's one of the big things in choosing the curves that are good for pairing, right? Choosing a curve pairing friendly curves, right? What will happen if I use a point from the wrong subgroup group? I am assuming you are talking about when we do, like, when you want to calculate, I guess, full torsion or like pairing groups. Um, if you use a point from the wrong subgroup in this scenario, I think what will happen is essentially when you want to do the well pairing, when you want to like do this function, when you want to calculate this, it will just give you incorrect value. If your G2, let's say you have like a bad point in your G2, um, like it will just not work, right? This I do not know the exact derivation, how this comes from, but I'll assume so this relies on a property from pairing groups and full torsion groups. So if you have the incorrect set here, this will just not work. It will just not give you the correct result that you want in this case. Yeah. So back to how to know if a curve is pairing friendly. Um, Pairing friendly usually just refers to curves that are, well, it's a curve that you can do pairing calculations on relatively efficiently. So in that case, you like to know if it's pairing friendly, you have to essentially see that one of the things is, yeah, the embedding degrees one, probably a lot more than that because there's a lot of things affecting um the pairing calculation efficiency. One of them is the embedding degree. So if you want to know, you probably have to just do the calculation and see if that curve is suitable in this case. Yeah. I don't have a list for that, I think, in this case. Let's see. Yeah. So if you choose a curve that, okay, so that remember Short-Weierstrass, Montgomery, and Twisted Edwards. So we talked about how Twisted Edwards, it's very easy to do a calculation for like addition because of um the fact that because of the fact that where is it? Yeah, the group law, it's very easy to do group law for the Twisted Edwards curve, right? Um, if you choose a curve that is a Twisted Edwards curve, um, you reduce the cost um when you want to apply group law, and that helps. In a sense, it helps you make if you're using it for ZK or for Snarks, it will make it so that it's cheaper to do group addition, right? Group operation, group law. Um, Short wire source curve is a lot more expensive to do because it's very hard to represent that in this case. Um, because you need to do branching. Same goes to Montgomery, right? You need to do branching. You need to specifically handle branching for the group law. I think for wire straws, it's even harder because it's very hard to define the. It's hard to define. It's also expensive to calculate the group law. In short wire straws curve case, it's a fine group law, right? This chord and tangent rule. So I guess yeah, that's one of the things to make sure your curves are pairing friendly. How to know? Yeah, one of the ways is yeah, see if you can make it a twisted Albert's curve or a Montgomery curves. Um, yeah, and also yeah, embedding degree of course, and probably a lot more. I will take a note on this, and I will give you a little bit more context on this probably next week. Let me just record this. Okay, any more questions? I hope I help answer ZK's and Xiao Mao's question. Okay, throw an increment again. Um, so if you can read Python code, this helps you understand a little bit more. Uh, yeah. So this essentially it's trying to hash. I wouldn't say this is brute force, but essentially it's trying to like this method, try increment essentially it's trying to hash some value into the curve. We are just checking like, hey, if these points work, if this works, so this is the I believe this is the Weierstrass, the short Weierstrass formula, curve formula, is it? No, I'm not. I think I'm wrong. Yeah. Um, yeah, I think I'm slightly wrong. Uh, yeah, I think I'm wrong. Yeah. Is it? No, it is. It is. Okay. Yeah, it is the short Weierstrass curve formula. But yeah, this is essentially trying to hash into a specific curve and see if this point works by essentially checking yeah if it's correct. In this case, yeah, it tries to hash into it. The first time gets 15, doesn't work because it's not in 3, 13. Tries the second time after you increment by 1. So the binary counter is used. Where is it? Binary counter. C, right? Yeah. Yeah. It's so you concatenate your basically you concatenate your primary counter. This will be increased and retry again. And yeah, this will constantly so this try and increment because you try to hash it in, and then if it doesn't work, you increment this specific bit and then try again with that additional bit uh for the target or your string or the word or the plain text that you want to hash into the curve. Yeah. So in this case, you'll just keep doing it and then checking this against the short Weierstrass equation. And yeah, yeah, it just keeps incrementing it until it gets a correct point. That's why I try and increment. Yeah. You can also try and implement this, not increment this, implement this, and yeah, and see, tell and submit the PR, right? Okay, so 5.6, constructing elliptic curves. This is a lot of math, this specific section. We talked, so there will be like trace of Frobenius, yeah, where you use this to calculate, um, well, you use this to check if your curve have more points than the underlying field. Um, yeah. We need this to do the complex multiplication method, which is talked about. Yeah, there's also J invariant, which the books mention. Um, yeah, both of this is used later in the complex multiplication method. I haven't really gone through this myself, um, but this is essentially a way for you to create an elliptic curve. So you might want to do this when you want certain properties for your curve. There are, okay, so I'm not exactly sure which of the curve currently up used in production is calculated via this. I don't know exactly which of them are done via this. Um, but for example, sometimes you might want a curve that allows you to do recursive operations a little bit more cheaper, or just allows you to do like recursive stuff, right? And yeah, or like aggregated stuff. In those cases, you might want to have your own curve with some property. And yeah, this might be helpful to do that. Um, a very interesting curve is the pasta curve, which is used by, I believe, um, Mina. Yeah, I believe it's Mina. Um, no, it's not Mina, is it? No, it's not. Is it? Yeah, but I don't quite remember. But essentially, um, yeah, pasta Vesta curve, the pasta, so yeah, pasta curves, something Vesta. I don't think it's pasta Vesta, something Vesta. But yeah, it's essentially um curves that are used um to enable recursive snarks. Yeah, quite interesting. You can take a look. Yeah, not sure if they are like they are actually constructed via this method, complex multiplication method. Yeah. Yeah, any questions or anyone that want to like talk about this? They have gone through this and want to talk about it? Welcome. So ZK asks, so the hash is just keep trying until it lands on a valid point. For this specific method, yes. Um, you are essentially so you still try to okay, if you look here, right? You have your string or like your plain text, you try to hash it in and see after you hash it in and you want like you convert to binary, does it hit? Does it land on a point within the curve? If it doesn't, we increment the counter and try again. This specific counter is also concatenated to the to the plain text or like the string itself, like the thing that you're hashing, right? The value, the word. So yeah, it's deterministic in the sense that the same value hashing to the same curve will always result in the same um hash because the counter will always be the same, right? You are trying and incrementing. So yeah. Yes, it is just keep trying until it increments until it finds a point, valid point. Pretty sure maybe there is a better way of doing it, but it doesn't really talk about it here. Yeah. This is a little bit different from if you're just doing on a field. So for the field, you can use you don't need to try increment. I believe there is something called, wait, let me check. No, it's not here. Common rings, hashing into module. Yeah, there's also try increment in rings as well, which does similar things. Um, yeah, this essentially does the same thing, but this is for rings and in fields. It works for that. If it's in groups, so yeah, this is the third method, right? They talk about third method here. But essentially, when you hash into modular arithmetic, you can do multiple ways of like doing it. Um, yeah, there's a few explanation here. So yeah, this is one of the things, right? They talk about hashing into a ring. Fields are essentially just um rings, two rings, I believe. Is it? Yeah. No, it's just ring. It's just a ring. Yeah, fields is just ring with the extra points, the extra infinity points, extra no, not infinity point, yeah, identity points, I believe. Yeah. Yeah. So they do talk about here, but for elliptic curves, you use the same method, but you are trying to hash into the points of a curve, right? Instead of the possible coordinates of a ring, you are hashing into the possible coordinates of a curve, which is slightly different because yeah, because of the selection of your generator in this case. Yeah. So yes, the try increment, yeah, it's essentially just keep trying until you find a valid point. Um, it can be very efficient because if your field is pretty large, or like if the your elliptic curve, the points in your elliptic curve is pretty large, um, there shouldn't be too much collision, I suppose. Or it should land, like when you hash something, it might just very easily land within that field itself, or like the curve itself. Yeah, intuitively for me, at least. Mm. If you're just hashing into groups, it's slightly easier. Groups is a little bit more straightforward. Okay, any more questions? So there's also this BLS 66 pen and paper curve where you can try to calculate. So they actually walk you through the entire calculation using complex multiplication method to basically create a curve, right? I haven't gone through this yet. So if you have and you want to share, please pick up, or else we will talk about this next week. We'll try to go through this together next week. Yeah. So without further ado, let's go back again. Any more questions within like for 5.4? 5.5 and 5.6, probably not 5.6. I'll go through 5.6 next week again, alongside with your possible implementation on elliptic curve and elliptic curve pairings. Um, yeah. Any more questions before we potentially end today's session? Okay, I think I'll assume that everyone don't, as of now, have much questions. Um, I'm okay, so it's been a few weeks. I've been conducting lessons by basically going through each section and then answering to questions. You have to tell me if this works for you or you might prefer some other way of going through the sessions itself because it's a study group. So yeah, just give me any feedback you have. You can PM me on Telegram or whatnot as well. Yeah, to tell me that. Yep. So without further ado, if there's no questions regarding this, please do try to implement what you've learned in chapter 5 in the language you choose. If you are familiar with Python, use Python. If you're familiar with Go, use Go. If you're familiar with Rust, use Rust. It's a homework. There's no pressure, of course. But if you are someone who learns by example or by implementation, this will help you a lot. Yeah. So let's talk a little bit about what we'll cover next week. So next week, we'll cover 5.6 and the entire chapter 6. So the entire chapter 6 here, it's chapter 6 is considered a shorter chapters, but it talks about statements which we'll talk about. It's a little bit, it's slightly related to compilers in a way, but also how you can represent your program, I think, in this case, a snark circuit, right? Um, yeah. So we'll cover 5.6 and chapter 6 next week. Um, Same time, 8 to 9:30. And if you have any questions or things that you want to know or learn about or like revisit from chapter 3 to chapter 5, bring it up next week as well. Yeah, we'll also, so next week will be a slightly longer session. I might run it to 10 p.m. next week. I'm not sure yet. We'll decide based on how fast we go through it. But we'll also additionally cover things that you have implemented for chapter 4 and 5. And I'll go through an implementation as well. So before then, you can submit your PRs to the repo. I'll try to go through them within the week and give some feedback or like, just have some discussion over there as well. So yeah, I think that's essentially it for today. So next week we'll cover 5.6. We'll go through specifically BRS 66, the pen and paper curve. We'll go through this. We'll probably go in a little bit more detail as well on what's covered here. I'll answer some of the questions you guys asked this week as well. And then we'll also cover chapter 6. So please go back, take a look, go through 5.6 and chapter 6, and we can have more discussion next week. Yeah, try to implement it in the language you choose, submit the PR to the repo. If you don't know what repo it is, I will share it again later in the group. Thank you very much for today. Thank you guys for
And
coming.
bye bye.
Okay, bye bye.